Good afternoon and welcome to the second in our Building Zero Carbon webinar series. Today's webinar is going to focus on the design of new and existing buildings and how they can assist net zero carbon at scale. So the previous session that we held in November was very much looking at how an individual building can achieve low carbon and energy operation. In today's session, we're going to be looking at how that can be rolled out at a national scale. So for those of you that don't know me, my name is Richard Tibbenham. I'm the director at Greenlite Building Physics. I'm a thermal modelling specialist. Quick overview of today's session. The session will last about 45 minutes and there'll be a Q&A at the end. We will look at what composes the UK energy mix. We'll look at what the implications are of replacing fossil fuels with alternatives as we transition to net zero carbon. We'll look at heat pumps and what the opportunities and limitations are with heat pumps. We'll look at the balanced pathway to zero carbon proposed by the Committee for Climate Change. We'll also look at the role of energy storage in new and existing buildings in low carbon strategies. So, the challenge that we face concerns the fact that in June 2019, the UK signed up to laws which oblige it to be a net zero carbon country by 2050. And that will reduce all carbon emissions to zero. So the target will require the UK to bring all greenhouse gases to net zero carbon by 2050, and that compares with previous targets of at least an 80% reduction from 1990 levels. The Climate Change Committee released their 6th carbon budget report in December, and that illustrates how the UK could practically deliver on this target.
Sorry to interrupt, Richard, but you're not sharing your screen with us.
I'm sorry, Nikki, am I not?
No.
Right, do apologise. Right, let me start from the top. I do apologise. Right. Okay. Right. Apologies for that. So we can see in the graph on the right here, the target is to achieve net zero carbon operation by 2050. Currently incurring about 8 tonnes of CO2 per person per year. This needs to reduce to about 3 tonnes by 2035, tending towards 0 tonnes by 2050. This aligns with the Paris Agreement, which is to hit no more than a 1.5 degree increase in global temperatures. So I'm just going to hold a quick poll, and I just want to ask how confident you are that the UK will deliver on these targets. So the poll's open for voting now. A few more pessimists than optimists by the look of it. We've got a few more coming in. Let's just wait for. Right, I think we're okay. So it's about it's a close call, actually. The majority of you are not confident we're going to achieve it. It's slightly more than those that are somewhat confident. Nobody is very confident, and a handful of you are not confident at all. So that's quite interesting. We'll revisit that at the end and then see how you feel about things then. Okay. So where does the energy to fuel our buildings currently come from? Well, we derive our fuel from natural gas, electricity, heating oil, bottled butane and propane, biomass like wood burning stoves, etc., and coal. The vast majority of fuel used in the UK for heating purposes is via a gas central heating system. That's around 85% of respondents to a BEIS study in 2019 agreed that their heating system was via gas. Oil was about 6%, and then various modes of electrical heating also compose 6% as well. So it's really natural gas that we're largely reliant on at the moment. If we look at how the UK energy mix is composed, this is from data, 2017 data, you can see that about 62% of our energy is derived from natural gas. Then a further 14% is used for natural gas that runs combined cycle gas turbines, about 8% from nuclear, fuel oil, wind, coal, and then various other segments, including solar, which compose the remainder. In terms of where we get this gas from, we used to be net gas exporters around the turn of the century. This has diminished now. We derive about half our gas from imports and half from UK native production. And then from the gas that we do import, the majority comes from the North Sea, from Norwegian fields. The remainder coming from Qatar and other countries. Gets a small proportion from the Netherlands and Belgium, which is ultimately fueled from Russia and further afield. So if you look at a natural gas flow chart of gas coming into the system of the UK network and coming out, you can see that about 20% is used for commercial applications, 30% in domestic use, and about 28% for power generation. The remainder is used for other industrial processes, and there's a degree of distribution losses as well. So if we look at an annual graph of where we derive our power from, with months January to December across the bottom, and gigawatts per hour of energy demand up the y-axis, you can see that coal forms a base load, only really present during the winter. This is supplemented by biomass. This is Drax Power Station, burns a degree of imported timber largely. Nuclear is fairly consistent year round. Very small percentage from pumped storage and hydro generation. And then combined cycle gas turbines provide the rapid response power generation. There's a very small quota of other sources. Some power from ICTs, they're international connection terminals. So that's imported power from the continent and from Ireland. Wind generation is forming a growing proportion. And then solar. So that's the mix for the UK electrical grid. By comparison, the natural gas consumption is significantly higher. And on top of that, we also have fuel oil usage for domestic heating systems. So all of this data has been kindly provided by Grant Wilson from the University of Birmingham. It's based on the year 2017. And this has been averaged. So this is 24-hour averaged data. So the snowy weather that we've got today is quite timely to make the points that I'm looking to achieve today. This is a screen grab from GridWatch from yesterday, and this illustrates that the majority of power was provided by combined cycle gas turbines. We had the nuclear generation providing that base load at the bottom there, and then various other segments providing the remainder. You can see this small flash here in yellow is the solar contribution. That's solar PV generation. So by comparison to the remainder of electrical generation during a cold, fairly dark winter's day, it's pretty minuscule. If we look at the data across the past month, you can see that again, it's the gas generation that forms the rapid response power generation. Nuclear provides this constant base load, and then on these windier days, like we can see here, when we've got some good wind generation, we're able to pull back the gas generation and save on those gas emissions there. So all this information is freely available from GridWatch. If you'd like to go and take a look at that, it provides real-time data as to what the performance of the grid is. So as you can see, the mix of generation sources that go into the grid vary over time, and they do and as a consequence of that, the carbon factor, so that's the amount of CO2 produced per kilowatt hour, varies quite substantially from hour to hour and from day to day and throughout the year. So this graph here shows the real-time variation in carbon factor across the year. Quite difficult to see. So you can see that during the winter, the variance between the high and the low points is quite high. During the summer, that variance tends to reduce due to lower demands. So I've pulled out some 12-hour, 7-day, and monthly running mean averages, so we can make a bit more sense of this data. You can see that with these higher carbon factors in March time, this was attributed to the Beast of the East in 2018. And in the same year, we also had a heat wave between June and August. So you can see that manifest as a higher carbon factor during the summer. That will be due to air conditioning loads and cooling of information centers, that type of thing. So you can see that the carbon factor in July was almost as high as at certain points, into autumn and into winter. So these higher cooling loads can have some impact as well. It's not just about the heating loads. So we can see here what the actual electricity carbon intensity was in 2018. And by comparison, this is the current building regulations carbon intensity for natural gas. So we've got the electric grid, which varies substantially throughout the year, and then gas at 216 grams of CO2 per kilowatt hour. So we can see that during the winter, especially, and during these cold snaps, the power from the grid is substantially more carbon intensive, but there's also periods during the summer where it is significantly lower. Now, as it stands, the building regulations carbon factor, which is used in EPCs and Part L assessments, is 519 grams of CO2 per kilowatt hour. So it is very outdated, and that provides a real disincentive to use electricity as a fuel source within new built buildings for compliance purposes, at least. Now, by comparison, the proposed level is 136 grams. So this is something of an aspirational level where I imagine they will be getting to within the next decade. So that we're going to move from an environment where grid electricity is heavily disincentivized via the compliance routes to becoming heavily incentivized versus gas. Now, as a consequence of that, the usage of electricity will become more incentivized. However, grid export via solar PV, for example, will become less incentivized, because rather than accounting for a export grid carbon factor of 519 grams, will now only account for 136. So it'll lose about threefold the incentive to export electrical power. By comparison, the proposed carbon factor for natural gas is only marginally lower. So there'll be very little change in incentivizing gas. So it's quite interesting looking at this. We're moving to a very different environment. We're moving from an environment where regardless of the time of year and the time of day at which we use energy, doesn't really have much impact on the carbon factor, in this case of gas. We're now moving to an environment where the carbon factor fluctuates significantly throughout the day and throughout the year, so that there will be a lot of incentive to use power during periods where that carbon factor is lower. So if we now look at this at more of a micro level across a fortnight, you can see this period here is displays a day. We can see that the natural gas demand curve fluctuates significantly. Tend to have these load spikes, one in the morning and one in the evening. And that's when people get their heating systems going, they get up and have a shower, that sort of thing. It tends to back off during the middle of the day when people are out at work. Then overnight we have a lull as people turn their heating systems off and there's less usage. So that represents about 130 gigawatts of power, and the gas grid can quite rapidly ramp up supply to meet demand. By comparison, the electric grid, it does incur a similar profile. Do have these morning and evening load spikes, but it's much less pronounced. And that only equates to about a 20 gigawatt range. So the majority of that, as you can see in the graph here, is accommodated via combined cycle gas turbines. So that provides that rapid response power generation as and when it's needed. If we now look at the carbon intensity of electricity throughout that same period and the cost, we can see that the two are quite heavily correlated. During this earlier part of the graph, you can see that there's more coal generation and more gas generation. That attributes to the higher carbon factor. As a consequence of that, the cost, the wholesale cost of that power is somewhat higher. We also have these lower carbon factors and lower costs during the night. So there's a heavy correlation between the two. If we now look at the average air temperature, this was taken from London. You can see that the two are inversely proportional. So where the air temperature is lower, in this case, we're incurring some sub-zero temperatures. We needed more generation, power generation, and that was brought in via coal-fired power stations. That increased the cost and the carbon factor. As the temperature rises here, we also have more wind generation through this segment here. We see that grid carbon factor tail off significantly. So it's quite a lot actually. We're looking at a carbon factor of about 450 here, and it reduces down to as low as 100 here. So 4.5-fold reduction in the carbon intensity. Compared to this gas, the carbon factor and the price of gas doesn't really vary. The time of use doesn't matter so much. So if we now look again at this 24-hour average data, this doesn't take into account these peaks and troughs that we see through a day. This has ironed out those peaks and troughs because it would be difficult to view on the graph. What I have done, however, is now use the 24-hour maximum data. So if we look at the maximum energy demand to supply infrastructure as we need it, it looks somewhat more like this. So the gas contribution, you can see that it's somewhat higher, and also this power generation from combined cycle gas turbines is higher as well. So we're really reliant on gas to provide for these spikes in demand that we see. A very significant dependency on natural gas for direct space heating and hot water. and also for grid electric power generation. Now, as we look to decarbonise the electricity grid, what we are most likely to see is a transition completely away from fossil fuels, substitution of natural gas with electricity. So we'll no longer be using gas boilers in homes, we'll be using heat pumps and electrical systems. All vehicles will transition to electrical power, and we'll also fully decarbonise the electricity grid over just 30 years. Core challenges include reducing energy demand such that we can actually provide enough power via electricity to run our infrastructure. Transitioning to low carbon space heating and electrical vehicle infrastructure, going to be a lot of upheaval and a lot of work in power distribution, power generation, changing heating systems and so forth, and changing the way that we power our vehicles. And then also alignment of energy demand profiles with renewable energy generation profiles. We'll discuss this in a bit more depth later on. And also electricity grid decarbonisation, and that will include carbon capture and storage strategies, whilst at the same time ideally keeping everybody happy as well, so keeping our fuel bills in check and so forth. So the Committee on Climate Change released their 6th carbon budget this December, and in this report some of the highlights are that it proposes all new buildings should be highly energy efficient with low carbon heating from 2025 at the latest. Didn't go to the extent of specifying anything like passive house as such. It just sort of left that fairly open. It's highly energy efficient. We'll be looking at a steady transition away from natural gas by 2050 for all but power generation. There will be some natural gas still used for combined cycle gas turbine power generation, but that will be equipped with carbon capture and storage systems. There's a very heavy emphasis on heat pumps for low carbon space heating. As we saw from the graphs previously, it's really the wintertime period which is the big challenge. It's transitioning that gas load to electricity. The summer is less of an issue. We have 4-fold increase in offshore wind capacity by 2030, and this is on path to a 6.5 to 12.5-fold increase by 2050. So very large increase in wind generation. And energy efficiency in over half of homes by 2035. So this is various insulation measures, low carbon heating systems, and so on. Now it proposes that the total energy demand of the UK will actually fall by around 33%. However, the electrical generation will actually increase by about 50% up to 2035. It may be even double or even triple by 2050. So we can see from the proposed pathway to zero carbon that heat pumps are going to be one of the go-to choices for decarbonisation of the building sector. You can see in green there, they expect that the large proportion of decarbonisation of the building sector to be provided via heat pumps. And they expect to see an increase of about 115-fold in heat pumps between now and 2050. So that really does form a foundation for the decarbonisation of the building sector. Here we can see the proposal to reduce gas usage in buildings to zero by 2050. There will still be gas used, shown in yellow and green there, for power generation. As I said earlier, that will be combined with carbon capture and storage. Electricity demand could increase by 2 or 3-fold between now and 2050. So very big infrastructure changes, and heat pumps are going to form a big part of that. At least that's the proposal. So I think most people understand the basics of how a heat pump operates. I don't really want to go into too much detail on that. What I do want to look at is what the implications are for mass deployment. So heat pumps operate best at lower flow temperatures by comparison to a gas boiler. That's flow temperatures below about 45 degrees C, ideally. That makes them best suited for oversized radiators and underfloor heating. For hot water applications, a storage cylinder is necessary. We can't have on-demand heating of hot water like you'd expect from a gas combi boiler. And at scale, heat pumps present a significant uplift in the demand for electricity, particularly during peak hours. And unlike a gas boiler, the heating capacity and the efficiency of a heat pump is affected by the ambient air temperature, at least for an air source heat pump. A ground source heat pump is somewhat more immune. So if we look here at the coefficient of performance of a typical heat pump, for anyone unfamiliar with what that is, it's the thermal output per unit of electrical power, or electrical input rather. So if I were to put in 1 kilowatt of electricity, I could expect to get out about 2.5 kilowatts of heat, just by virtue of the way that the system works. Now, a heat pump is more efficient when providing lower flow temperatures, so it can achieve a higher COP for space heating applications, so long as that's lower than 45 degrees in this case. For hot water heating applications, they are capable of heating water to higher temperatures, but that incurs more electrical input per unit of thermal output, so that the COP is lower. So I've selected this data from the example buildings that we looked at in our previous webinar. And based on the energy demands for space heating and hot water, I've combined these COPs into a single annual profile. So you can see that during the summer, the thermal output per unit of electrical input is somewhat higher. During the winter, it has to work that bit harder. So it's somewhat lower down there. So we're getting about 4 kilowatts of heat out for every kilowatt of electricity in during the summer. During the winter, that diminishes to about 2.2. So what I've done is I've looked at the existing peak demand for fuel oil and natural gas for space heating and domestic hot water generation. And I've created this profile of what the additional energy demand would look like if we were to transition fully away from gas as a fuel to electricity via heat pumps. So I can see there's a significantly larger amount of power required during these peak periods, during the winter especially, than is currently available, about 2 or 3 times more. During the summer, it's less pronounced because the system is more efficient and the demand is lesser as well. So this is the 24-hour maximum data that we're looking at here. So this is the maximum amount of power that we would require to operate infrastructure in the way that we currently operate it using heat pumps. So again, if we look at this at a more micro level across the same fortnight during the winter, that represents 1 day. That is the existing natural gas heating oil demand profile. That's now been removed for transitioning to heat pumps. And we've now got this zone here of additional energy, which we need to get from somewhere. Overall energy demand has been reduced quite a lot, but the electrical demand has risen. So the question is, where will we find this additional power? Bearing in mind that there will also need to be power for electrification of the transportation network as well. So I've presented here what a future scenario might look like in 2050. Remove the coal generation completely. We do maintain the same level of electrical generation using gas turbines, but that's now using carbon capture and storage. And we've increased the wind generation capacity by 6.5 times. That's the former oil and gas profile. So we can see even with this very large increase in the amount of wind generation, there's still periods where the heat pump energy demand exceeds the generation capacity. And likewise, there's periods when it's quite windy where the generation capacity exceeds the demand as well. So you've got these big fluctuations in supply and demand. Now, if we take a 24-hour average of the energy demand, we can see that we lop off these daily peaks and troughs in demand. If we take a 72-hour mean average, you can see that that line is even more ironed out. So if we were to employ energy storage, we would be in a position to charge up that storage during periods when the supply exceeds the demand, and we could draw down on it during periods where the demand exceeds the supply. Now, at the moment, we don't have much in the way of grid scale energy storage. We just ramp up and down the gas-fired power stations to accommodate the demand. But as we move away from gas increasingly, we'll be required to look more at storage. So to reduce electricity costs and carbon, firstly, we need to reduce demand such that we don't use so much in the first place. By doing so, that has a trickle-down effect that we need less energy generation and less storage capacity as well. We also need to align the energy demand profile with the energy generation profile. We'll talk a bit more about that later. We need to reduce the energy import during periods of peak demand. So if you have a poorly insulated house, for example, with electric heating that you need to use on a day like today throughout the whole day, that will incur a high carbon factor and a high cost. If you can avoid that, you will reduce your cost and you will reduce the carbon intensity of the grid. Likewise, if you are in a position to export power on a day like today, you will be able to export power when it is highly valuable. So you'll be able to increase your yield from energy exports. Now, these principles are just as applicable at a micro level as they are at a macro level, so that they're as applicable to a single building as they are on a national scale as well. So we've seen here how energy storage can allow us to ride out these fluctuations in differences between supply and demand. As we increasingly move across to renewables, the generation from those renewables is more fluctuating, and we need some capacity with which to absorb power and then discharge it when we need it. If we were to just provide enough wind turbines that it catered for supply at any time, we'd be over-specifying the wind generation such that we only used it fully on the coldest of days. So that's not cost effective. So that there will need to be something to address the storage requirements. Now, there's various options available. There's options at a grid scale. So there's hydrogen electrolysis and storage. So this can be done in the UK or overseas. So this is the cracking of hydrogen using green electricity, then use that hydrogen to run through a power plant, which can then create green electricity using hydrogen. So we're using hydrogen in this case as a means of energy storage. There's also some more extreme systems which are being developed. This is a system which has been developed in Switzerland. It's called the Energy Vault. Basically involves thousands of concrete blocks which are lifted up and down using a tower crane type system. As it lifts the blocks up, it uses power. So it's using power when there's an energy surplus. As it drops the blocks down again, the gravitational energy drives generators within the motors of these little winches, and it provides energy export. You've also got grid scale electrical battery storage. This is a system in Australia, which is provided by Tesla, and that is tied in with this wind farm. You've also got behind meter energy storage. So this is within a building. The most common is hot water cylinders and thermal stores. You can also use phase change material thermal stores and electrical batteries. So if we look at a quick breakdown of the differences between different types of in-building energy storage. The cheapest mode of energy storage is water. So this cylinder here will cost about £1,400. We can input thermal and electrical energy into the system. We can use biomass stoves, heat pumps, electric immersion heaters, you name it. It can absorb a lot of different modes of energy input. The phase change material system, this is a system manufactured by Sunamp. It's about the same capacity. It's about twice the cost, but it's about half the size. So these are very applicable where space is of a higher priority than cost. In terms of the inputs and outputs, it's fairly similar to a hot water cylinder. And then finally, we have electrical batteries. Again, it's about the same capacity, but it's about twice the price of a phase change material store, and about 3 or 4 times more the price than a hot water cylinder. Likewise, these are only capable of absorbing electrical energy inputs. So it'd be no good if you wanted to use a air source heat pump, for example, to power an electrical battery. It's only really going to accept power inputs from solar PV and wind generation. So you can see there that the cost of electrical batteries especially is quite prohibitive for the majority of people. You can get the same amount of energy storage capacity in a 260 litre hot water cylinder. So in terms of what I'm doing at my own home, I've built this SIPS outbuilding, heavily insulated structure, 150 mil SIPS. And my intention is to use this part of the building here for energy storage. At the moment, I'm intending to install 2 500 litre thermal stores. That'll have a useful energy capacity of about 50 kilowatt hours, sorry. Cost is £3,200, and that's the equivalent of about 4 Tesla Powerwall 2 batteries, which would cost close to £24,000. So you can see that for mass energy storage, it is significantly cheaper at the moment to use water as a storage medium rather than electrical batteries. Now, electrical batteries do have their place if you need electricity, maybe in an office type environment. But I think in dwellings, the majority of energy is used for thermal applications. So it makes sense to keep it in a thermal mode of energy. So into those thermal stores, I will be inputting solar thermal inputs, air source heat pump inputs. I've got a wood burning stove, a back boiler that'll feed into it as well. That's really good for the heat pump is good at providing low grade heat, so 45-degree flow temperatures. The wood burner is that's better at pumping out higher flow temperatures, so we can configure these stores to make best use of these. I can also feed in some solar PV via immersion heaters if there's any energy surplus from a PV array. So at the moment, energy storage is currently fairly detrimental to building regulations energy assessments. It doesn't, it provides a negative impact. I think with time, the relevance of energy storage will become more acknowledged, and that will feed into regulatory compliance procedures. So alternatively, or in addition to energy storage, we can also look at some smart control options. So time switches is a simple one, or shifting power from peak rates to economy 7, for example, using power in the night to heat up a hot water cylinder and then draw down on that cylinder during the peak periods during the day. There's also some more advanced BEMS and equipment control systems which can regulate power to plant and equipment, like a fridge, for example, based on the price or the carbon intensity of the grid at the time. So this latter system requires quite a high level of real-time information connectivity. So it's using the internet to establish what the carbon intensity and the prices of electricity at any one time. It will also look at what the demand is for power within that system, and then it will regulate load accordingly. So I think this is going to form a real big growth area in the industry, these smart controls which power up and down kit, including cars for that matter, accordingly. Then there's also flexible rate tariffs. If you want to make use of these lower costs during off-peak hours, you need to be using a flexible tariff, which is based on the wholesale price of power. So I've mentioned a handful of times in the session that we'll be looking at the alignment of annual energy demand and energy generation profiles. What I mean by that is, at the minute, we can see here that the energy mix is composed by the electrical grid along the bottom there. That's about 55 gigawatts peak, and the natural gas input for domestic space heating and hot water, which is much higher. Now, as we transition to electricity, we'll be more reliant on the electricity grid, obviously. At the moment, it's fairly flat. We don't generate a huge amount more power during the winter than we do in the summer. Likewise, solar contributions are lesser during the winter. You can see in green here that they're slightly higher during the summer than they are in the winter. So it's not really a big business argument for the use of solar PV in the UK environment. Now, for those of you who saw our webinar in September, we looked at a future home standard dwelling, and I produced this energy demand profile for that building. Now you can see that there's quite a curve on that profile. During the winter, it consumes about 7 times more power than it does in the summer. If we compare that to the passive house option that we looked at in the same seminar, you can see that reduces to about 2.9. So this much flatter annual profile is a lot more sympathetic to the use of the electricity grid for powering. This profile with a steeper curve is more reliant on gas. So it's going to be a lot more difficult to transition this profile than it will be compared to this one. So this is a a real big issue which I think has been overlooked quite a bit. It's not all about just the annual demand for power. It's how it's distributed across the year as well. Now, there is quite a large challenge, and that is at the moment gas is incredibly cheap. It's about less than a quarter of the price of electricity. In fact, if we look at this graph here over the last 10 years, you can see that gas is cheaper now than it has been for the last 9 years. It's only really this point back in 2010 when it was somewhat cheaper. So there's very little financial argument to actually switch across to electricity, even if you're using that electricity in a more efficient manner. So this is something of a hurdle. So in order to encourage this transition, which I think we all accept is necessary, the Climate Change Committee, they propose the following implications and recommendations. In terms of building regulations, all new buildings will be required to achieve very high levels of energy efficiency and use low carbon heating by 2025 at the latest. So we've spent the last decade with very little change to energy efficiency requirements of the building regulations. There have been efforts to raise them, but we were expecting to have zero carbon dwellings by 2016, but that was all kicked into the long grass. I think now that's catching up with us increasingly, and we're expecting to see changes to the building regs by the summer of this year. The adjusted gas and electricity carbon factors, which we ran through earlier, will heavily incentivize the use of electricity as a fuel source for new build, and it will also disincentivize the application of solar PV. It won't achieve those carbon reductions that are currently the case. Now, here's some of the more interesting things. It suggests that by 2028, all rented homes would be required to achieve an EPC Band C rating. There's a lot of work there to modify the rental sector. And even more interesting, domestic mortgage lending requirements will be required, and that they'll require a Band C rating from 2025, well, between 2025 and 2033. So if you want to take out a mortgage on your home, it will have to achieve a minimum requirement of energy performance, which no doubt will cause some political upset. All homes for sale to achieve a Band C rating also by 2028. So it's only 8 years away that will be required a Band C rating for all home sales. Now you can imagine that the type of impact that this will have and quite how politically palatable it will be. Also talks about reform of the EPC assessment as well to better reflect reality. I think that's really essential. I think a lot of us know that there's this performance gap between reality and prediction, and there will need to be money pumped into modifying this assessment process accordingly. Sale of gas boilers we phase out from about 2033 for domestic and about 2030 for commercial. And all oil burning boilers will be phased out by 2028. Again, that's for domestic, and 2025 for commercial. Also talks about energy prices to favour a shift to low carbon technology via tax incentives. Now, to date, the government has been quite reserved on taxing carbon. We can see that the cost of gas, although it has a higher carbon factor, is significantly less than electricity. Now, there will become increasing pressure to address that imbalance and try and incentivize the use of electricity more so if the government wants us to transition to this zero carbon economy, which they are legally signed up to. So what can you do as designers to address the topics raised in today's webinar? Firstly, you can implement energy demand reduction measures. this really has a trickle-down effect. If you can reduce the energy demand, you reduce the energy generation requirements. When you reduce the energy generation requirements, you also reduce the energy storage requirements. So that reduces cost down the line. So we can use energy efficient architecture. This was a topic which we went into in November's webinar. If you didn't catch it, I will leave a link at the end of the video. We can use passive solar heat gain, for example, to significantly reduce heating loads in new buildings. We can use roof designs to optimize the performance of solar technologies and so forth. We can also align the on-site energy generation profile with the energy demand profile so far as is viable. I will be holding another webinar to address that specific point. Insulation, air tightness, heat recovery, ventilation, LED lighting, and passive house, and so on. All these measures will reduce energy demand. Plant selection also. Moving to a high efficiency heat pump, for example, reduce your energy demand versus electric panel heaters. We also should be looking at reducing peak energy loads and provide supply and demand flexibility. We can do that via the energy measures, energy efficiency measures noted above. So if we just use less energy in the first place, that makes the situation a whole lot better. We can also use energy storage, as we discussed, to ride out these fluctuations in supply and demand profiles, and smart system controls to achieve similar, not quite as good outputs. Now, it is important to note that current and emerging building regulations only generally account for an average carbon factor throughout the whole year. And this is not representative of the reality. Now, as a consequence of this, we've incurred sort of misallocation of resource. I think PV is quite a good example. It's been heavily subsidized, encouraged. It's not really particularly suited to a UK environment. Based on the existing building regulations assessment structure, the benefit of energy efficiency is generally underplayed. That is because it accounts for this annual average of electricity carbon factor. If we use the seasonal carbon factors, you realize that saving a kilowatt of energy during the winter is a lot more effective than saving a kilowatt of energy during the summer. Likewise, exporting PV generation during the summer when the carbon factor is low is not as effective at reducing carbon as the assessments would make it seem. So we can use a dynamic thermal model with variable carbon factors to provide a more realistic tool. And I would advise anybody who is looking to achieve net zero carbon to give that some serious thought. So I will hold a second poll now for those that are still with us, and I will inquire, given the evidence that you have seen today, has your opinion changed any on your confidence levels in the UK achieving net zero carbon by 2050? Interesting. Well, that's, I'll just share those with you. So the majority of you are somewhat confident. We seem to have got an increase in those who are have no particular persuasion, and 4% now are not confident at all. So I think some of the information that you've seen today was probably presented a more negative outlook than had formerly been the case. So that is interesting. Like I say, this video will be uploaded to YouTube tomorrow. So if any of your colleagues want to watch it, you can send them the link. So just a quick reminder, we do provide a free 30-minute design review, and we hold a design clinic on the first Friday of every month, which is also free. So I will send you all an email tomorrow with some links to hop onto those should you wish to. The next session, which we will hold in March, will be looking at low and zero carbon heating systems. So a lot of this will be looking at this alignment of supply and demand and how storage can feed into that in a bit more detail. So that is the plan for March. So it is 25 past now, and time for some Q&A. So if you would like to come in, Nikki, and if we do have any questions.
We have a few questions. We've got one from Andy Clark. So he says, obviously storage will be needed. Mm-hmm. At what level of the system is it best?
Well, pros and cons. I think there's often an assumption that somebody else will sort out all these problems for you. So if we go down that road and just expect that the utility providers will provide all this, it will be larger scale stuff. But there's not been any demonstration as to what that would look like at the sort of scales that we're talking about at the moment. Likewise, those costs will inevitably work their way into your energy bill. If you can, if you want to be more, how should I put it, more independent in the way that you deal with these matters yourself, then you can do similar to what I'm doing and employ those measures in your own home. That will allow you to only use power when it is particularly cheap. You'll possibly be in a position where you can export power when it's expensive, and you could, have a negative energy bill effectively. Now, I suspect that there will be economies of scale. So some of this, very large scale hydrogen storage, for example, will be more cost effective than shoehorning some large thermal stores into your house. But I think it really, I don't know, to be honest, what the figures are, because it's still emerging. I think possibly what we will see is hydrogen generation in the Middle East, Northern Africa, and so on, areas that have very good solar exposure. That could well be shipped to the UK, and then we can store it over here and use it as we need to generate power. So that might form part of the mix as well. But I don't know is the bottom line, I'm afraid, Andy.
Okay, so Peter Bates, he asks, what is the role of electric vehicles as a means of battery storage for the home?
Right, okay, yeah, so they will provide a degree of flexibility. I've not really gone into vehicles because I wanted to focus more on the building sector. They will provide some degree of storage. As we've seen, that electrical batteries are very expensive for what they are. I think the other issue to consider with a car is the larger the battery is, the larger the weight of the thing. And subsequently, you need to haul that thing around with you whenever you drive around. So I think the new Land Rover Discovery Hybrid, I think it's 2.6 tons. So the efficiency of the vehicle diminishes as the battery gets larger. So there's kind of pros and cons to it. I'm personally in favour of thermal storage via water. I think it's quite tried and tested. And you don't have the issues with degradation of the storage either, like you do with an electric battery. But you would have to do some more advanced analysis on uptake of electric vehicles, how they interact with the grid, so on and so forth, to really establish what role they will play in energy storage.
Okay, another one from Andy Clark. I see an issue with people buying homes to do up and failing because they can't get a mortgage until they've done the work. Catch 22.
Yeah, well, I think there's going to have to be a lot of elaborate funding structures put into place to avoid this type of thing, because otherwise it'll just be political suicide. So there has been a separate report produced by the CCC. You can download that. That is includes policy recommendations. So there's a lot of stuff in there as to the role of finance and so on. I don't fully know quite how these systems are going to manifest. I don't think anybody quite knows at the moment.
Okay, so Alexander Wenzel says, in the case of lower income areas, what accessible alternative measures could be applied?
Well, it depends how far you want to go with things, really. I mean, we've seen a lot of PV put on over the last decade. It's a very easy plug and play system. Electricity is quite expensive, so the actual financial yield is relatively good. They're just not that great at reducing carbon. There's no real quick wins, to be honest. It's going to be a very expensive and potentially disruptive process. I think that the best that lower income homes can expect is funding of various sorts from government. I mean, like I say, there's more on that in the policy report. There will inevitably have to be financial mechanisms to support this. It won't all fully fall on individual homeowners to foot the bill.
Okay, and Daryl Hanley says behind the, I think that's meter storage, it did not mention storage heating. Any reason for that?
Not particularly. No, I'm sorry, Daryl. Yeah, you can use. You can. It was just keeping things within the half hour, really, or 45 minutes rather. Yeah, electric storage heaters, it's a very similar principle to heating up a hot water cylinder and discharging it overnight, a bit less controllable, but same sort of principle. I will cover that in more detail, Daryl, and by all means, if you would like to assist us in the session on low carbon heating, I would be more than happy to have you on board. Thank you.
Okay, and Felix Lang says, given that there is an existing gas network, would power to gas technology from hydrogen produced by wind not make more sense than the transition to electricity for heating?
Right. So yeah, good question. That no is the short answer. The issue is that if we crack hydrogen using green electricity and then use that hydrogen, you could theoretically use that hydrogen in the gas network. There are certainly issues with leakage, moisture getting into the grid, and also adaptation of boilers to use hydrogen. So it's not an easy swap, but it can be done. But the main issue is to do with efficiency. If you look at a typical gas boiler, the efficiency will be maybe as low as 60% for heating hot water. Compare that to a heat pump, and it's maybe 200%. So you would need twice as much green electrical generation capacity to go down that route than you would do down the heat pump route. So that is the reason why at the minute heat pumps are the favoured option. Okay,
so David Gilby asks, V2G trials are progressing well with various parties, sorry.
Sorry, say that one again, Nikki.
V2G trials are progressing well with various parties.
B2G. I'm not
V
too
for
sure.
Victor.
I'm not too sure what you're referring to there by B2G.
V for Victor.
Oh, V. V2G. Can you expand on that? I'm not quite sure what that one's getting at.
Okay, we'll move on to John Kellett.
Okay.
What are the best letters after the name to look for when seeking low carbon proficient M+E consultants for a design team?
Oh, good question. It does vary somewhat across the board. Personally, I'm a CIBSE low carbon consultant. I must be honest, the application process to get that accreditation didn't really involve a huge amount, so I wouldn't hold that in particularly high esteem. I'm also a CIBSE low carbon energy assessor. That does involve more in the process to get that. I think, to be honest, just look at reputation and experience. just look for examples of what previous projects people have worked in. I think that the whole industry is evolving so quickly that I wouldn't really peg too much on any particular qualification. I would be looking at experience more so.
Okay, so Daryl, to your offer of asking him to come along, he says no problem. Now back to David, it's vehicle to grid.
Oh, vehicle to grid, right? Okay, right. Okay, yes. Well, I mean, I dare say that it has its place. Whether or not it is sufficient capacity to ride out these undulations in supply and demand is you'd have to model it to see quite what that looks like at a national scale. You know, obviously the big issue that I've been trying to prattle on about for the last 10 or 15 years is just reduce energy demand. That's the core sort of route to allowing all these things to operate well. If we had, you know, a nation full of passive houses, for argument's sake, you could probably use electric vehicles as your sole means of energy storage, because you need so little energy in the first place. But the problem that we've had is we've built all of these very low performance, low efficiency buildings over the last 10 years, when we've had a good opportunity to build better, and now they're presenting these very high energy demands. They seemed cheap on the surface, but they didn't factor in the cost of transitioning across to a net zero carbon grid, and unfortunately the people that have profited out of that are not the ones who are having to pay for it. But that's a different story. But yeah, no, I don't say electrical batteries in cars will certainly play a role in this process, but I'm not quite sure how much.
Peter Bates asks, are ASHP really the main solution when they are very much dependent upon careful sizing up and good control by occupants being potentially a major problem?
Yeah, no, exactly. There will be teething issues, obviously, with all these things. But I mean, I think the reality is that if we want to achieve net zero carbon, like I mentioned earlier, it's not favourable to transition across to hydrogen and use that within the existing gas grid. So there are limited options, really. I think, you know, ground source is more efficient during the winter, and it's certainly be more efficient on a day like today. But there's costs and implications for space for that type of thing. So I think air source heat pumps will be the common mode. But you know, people will have to evolve, really. I mean, it's a bit like when we moved from coal fires to central heating. They'll have to change with the times.
And Andy Clark asks, addition of hydrogen to existing mains gas can reduce the carbon impact of gas heating without major change to system, only reducing impact. Yeah,
it can, but the issue is where do you get that hydrogen from, for a start? If you want to, you can create hydrogen from natural gas, but it still incurs carbon in so doing. If you want to create that hydrogen from renewables and create green hydrogen, then as I went over earlier, the amount of zero carbon green energy supply needs to be substantially higher to do that than it does for the heat pumps option. Also, I mean, we can supplement a percentage into the gas grid, but that isn't going to take us all the way to net zero carbon, which is where we ultimately need to be. So I think it's quite important not to just cherry pick the easy options and hope that a silver bullet solution will come along at a later date. I think there's been quite a lot of that over the last 10 years. Just whack a bit of PV on, put a heat pump on here and there. We've overlooked some of the more fundamental changes that are required, like reducing energy demand. I think if we just keep our eyes on the final target and have a structured approach to get there, then I think that the heat pump option is better aligned to that.
Okay, last one from Michael Williams. How would you apply variable carbon factors to your thermal modelling?
Yeah, tricky one. It's at the moment, it's not a perfect science. I'm using, you can get carbon factors, live carbon factors from carbonintensity.org website. The problem that I have is that I can't align the simulated weather file within a simulation with a carbon intensity profile as well. Now, I would like to see CIBSE deliver a combined weather and carbon file, carbon intensity file, so that all that information is cohesive. So that on a windy day, perhaps the carbon intensity reduces because there's higher wind component. I think probably the best that you can do at the minute is to just look at seasonal averages, sort of a seasonal day and night average, and then you can export data from your thermal model and run it through Excel or something and apply it that way.
Okay, Peter's come back with a reply on the ASHP saying GSHP is no good in urban areas. Are there new thermal storage systems powered by electricity likely to be a more simple solution than ASHP and requiring less expertise?
Well, I think for dense urban areas, the reliance will be more on district heating systems, and you may see ground source heat pumps with boreholes in those sort of applications, and they'll be taken on board, large scale stuff like energy from waste, and they'll include carbon capture and storage, that sort of thing. So I think for areas like inner London, it's not going to be viable to have even air source heat pumps in a lot of spaces. A lot of people haven't even got a balcony to hang a air source heat pump off. I think that there is going to inevitably be a lot of different solutions which best fit different scenarios. So I think we're going to see, rather than just this foregone conclusion that you will have a gas boiler, which is largely the case in most homes now, I think we're going to see a lot more fragmentation of different solutions for different applications.
Okay, Peter, just lots of heat from London Tube.
Yeah, I mean, there'll be that's ideal for feeding into a district heating system, pulling out heat from the tube. So like I say, there'll be different solutions for different applications.
Okay, and Jeff Bell says, is there not a balance between spending money upon improving property thermal efficiency versus cost of heat pump, i.e. spending money on property efficiency may give a better ROI than a heat pump?
Yeah, so there is, obviously, it's dependent on a lot of different factors. So in general, investment in the construction fabric is more costly. It has a longer payback period, but it will ultimately allow you to get to a lower carbon intensity and a lower energy demand. If you just put a heat pump onto a solid masonry building, for example, it will never achieve a particularly good performance. However, PV especially is fairly low cost, low disruption, and it's fairly quick payback period. Likewise with a heat pump, the payback period is shorter than fabric upgrades. Now, I did go through some of the paybacks in the previous webinar actually, and it was quite interesting to see that passive solar heat gain, if you have the opportunity to build a new house, just orientating your house in the right direction and optimizing passive solar heat gain is significantly more cost effective than PV and heat pumps for that matter. It all depends what the final goal is. I think that's what I'm trying to get at. If you want to achieve zero carbon at the end of the day, you will inevitably have to carry out some sort of fabric upgrade. If you just want to reduce your emissions by a small percentage, then the quicker paybacks are via renewables.
And Peter just mentions again, but there's not many tubes in smaller towns.
Certainly aren't, Peter. No, like I say, it's it'll be deriving power from where you can. I mean, there's a city in Norway that derives most of its heat from an estuary and runs that through a water-to-water heat pump and use that to heat the whole town. So there will be, you know, areas where boreholes and ground source heat pumps are, you know, more attractive. I mean, here where we're based, got a large waste incinerator that's destined to have some sort of energy from waste capacity and district heating set up with it. So it's all about a case of, you know, using what you've got available to you.
And that's all the questions, Richard.
That is the lot. Wonderful. Well, thank you for joining me on this snowy January afternoon. Do apologise that I wasn't showing my screen at the start there. And I hope to see you all in March. So I'll be off for now. Thank you.